So quiz 6 key. Um, hopefully recognize oxymercuration, polar product solvent. See where things are adding. Draw the H's in. First step, 3 arrows addition. Pi bond reacts with mercury. Breaks the O. Breaks the bond to O acetate. Lone pair comes back. 3-membered ring. I draw these two as wedges. The back two as dashes. Product solvent comes in. Does the SN2 on the more substituted side. Right, does the SN2 on the more substituted side. Again, these are the steps that are given to above. Nothing happens to those H's or that carbon, so we need to do a deprotonation. So we have H plus. Notice that they're anti to each other, but I didn't have to change the wedges and dashes. Last step is just that mercury gets replaced with H, gets you to this product. And now we ask ourselves, we've gone through this, did I make an enantiomer? You did not. This carbon is bound to this nitrogen piece, and then a methyl, and another methyl. So you did not make an enantiomer, so you don't need to worry about the other product. But always ask yourself, did I make an enantiomer? Not this time. So here, to identify this reaction, we have a Br2, which makes me think halogenation. Then I look at the solvent, and I see it's a polar product solvent. So that makes me think halohydronation, halohydrin. First step is the same. 3 arrows, 1 step. Pi bond reacts with bromine, breaks the bromine-bromine bond. Lone pair in the first one comes back, makes that 3-membered ring. Wedges and dashes come from the bromine if it came from the top. There they are. H and ethyl on the same side, they're there. Instead of having the bromine react, we have the solvent react, add in SN2 style to the molar substituted carbon. Get that anti-addition. Last step, we have a deprotonation to make H plus and Br minus. Right? And the other product you're missing here is just the enantiomer. All right, notice how I asked for the stereoisomer product for the reaction below. So it's the other enantiomer, that's what I was looking for. There. Did I draw the other enantiomer though? Oh golly, I didn't. Hold on. I was half paying attention when I did this today. My fault. Because I made it more complicated. I'll fix the key online. And I'll say there's an error in case anybody else was worried about this. It should be this. There. That makes more sense. Alright. I flipped them around way too much. Phosphorus and the same carbon. Both of them are just opposite sides flipped around. That'd be the other enantiomer. My fault. So let's go over why this one is wrong. This one is wrong because, right, phosphorus has to add to the most substituted carbon. It's never going to end up on the less substituted one, right? So that's just wrong, right? That doesn't happen. So that's why this one's incorrect, right? Now this one is correct because the phosphorus is on the more substituted carbon, but imagine instead of the bromine being on the top here, what if the Br was on the bottom? Then the phosphorus had to come from the top. That's what this is showing, right? So the carbon, the phosphorus is bonded to never changes, and I screwed that up. What changes is it the phosphorus on the bottom part or is it on the top part, right? And then likewise, if the bromine's up, the phosphorus has to be down because they're trans anti-products. Bromine's down, phosphorus has to be up. So this is why I screwed this up because I put the phosphorus on the wrong carbon. Sorry. So this is the enantiomer, right? Because we made asymmetric centers. We made chiral centers, right? This carbon is bound to 4 different things, and this carbon is bound to 4 different things. So when I say other stereoisomer, that means the other enantiomer, like the other stereoisomer, right? So if I made chiral centers, the opposite version of the enantiomer of this exists as well, and that's what this is. So right, see what I did? I didn't have to change my wedges and dashes at all. I just flipped around where the bromine and the phosphorus were at relative to each other, right?